This week, we're going to be looking into the topic of atomic structure. Now, we already have a general idea of the structure of an atom based on Rutherford's famous gold foil experiment, which showed us that an atom consists of a heavy nucleus at its center containing positively charged protons and uncharged neutrons, and then much lighter negatively charged electrons moving around in the periphery of the atom. And this picture that was developed based on Rutherford's work has really taken hold in the popular imagination, has pervaded popular culture. And our objective this week is going to be to develop a more sophisticated understanding of how atoms are organized and what their structure really looks like. And in order to develop this idea, we're going to need to distinguish between some concepts in the field of mechanics. So mechanics is a branch of physics which is concerned with how things move and change over time. And the concepts that we need to know about are particles and waves. Now, particles are things that you're probably familiar with. These are objects that are located at definite points in space. They have mass and other properties, and they typically move around. They can bounce off of walls. They can bounce off each other. And the key characteristics of particles are that, number one, they have definite positions and velocities. So you can talk about the coordinates of a particular particle in space. You can talk about how its position changes over time. And then all particles also characteristically bounce off of the walls of their container, and then they can also bounce off each other in collisions. So particles collide with one another and bounce off. Waves, on the other hand, are very different from particles. The most obvious difference is that waves are spread out in space. And so what you're seeing here is an example of a water wave. And there are also sound waves and light waves. There are waves in guitar strings, drum heads, all sorts of things experience waves. And in its essence, a wave is a disturbance of some kind that changes over space and time. And so in this case, the disturbance is in the height of the water level. In a sound wave, the disturbance is in the pressure of the air. And in sharp contrast to particles, waves are spread out in space. They don't have a definite position, and they tend to reflect off of walls when they are in a container. And waves, rather than colliding with each other, waves experience something called interference. And so these are major distinctions between the behavior of particles and the behavior of waves. And since you're probably familiar with the way that particles behave, we're going to spend the rest of this video looking more closely at wave behavior and talking about how to describe the details of how waves work. So here I've got a picture of three different waves. You could think of these as light waves or sound waves, or waves in pieces of string that are being waved back and forth, or waves on the surface of water. And we can describe a wave in a variety of different ways. One thing that is very easy to notice is there's a characteristic length of a wave. And so the distance from one trough to the next trough, or from one peak to the next peak, is called the wavelength. And in this picture here, the red wave has the longest wavelength, and the blue wave has the shortest wavelength. And then Another feature of waves is that they're not just oscillating in space, they're also oscillating in time. And it'll be a little bit easier to see that if I put up some contrasting rectangles here. And if you pay attention to the wave motion between these gray rectangles, you'll see that the blue wave is moving up and down the fastest. The green wave is moving up and down at an intermediate rate, and the red wave is moving up and down most slowly. And so all three of these waves are traveling with the same velocity. The speed that the wave is moving through space is the same for all of them, but the short wave is oscillating the fastest. The long wave is oscillating the slowest, and this is a characteristic property of waves. A wave with a long wavelength tends to have a low frequency. And if the height of the wave is the same, or if the amplitude of the wave is the same, this low frequency wave will have a low energy. And by contrast, a wave with a shorter wavelength, if it's moving at the same speed, will have a higher frequency. And if the amplitude is the same, it will have the highest energy. And you can sort of understand why the higher frequency wave would have more energy. If you imagine, trying to create these waves by, say, waving a jump rope back and forth, you're going to have to work a lot harder to move the jump rope faster to get that higher frequency of the wave motion. You don't have to work as hard to move it more slowly. And so at an intuitive level, the higher frequency waves are going to have more energy, assuming that the waves are, that the height of the wave is the same. And so the cartoon here is illustrating the relationship between wavelength and frequency for light waves. So the waves are not drawn to scale; they're magnified. But I am showing you the relative sizes of red, green, and blue light waves, and for an actual wave of red light, the wavelength is 700 nanometers. So that is much thinner than a human hair, but on the other hand, it is much larger than an atom. And then a wave of green light typically will have a wavelength of about 510 nanometers or so, and a wave of blue light will have a typical wavelength of about 400 nanometers. And there's some variation in this, but this gives you some idea of the typical wavelengths for visible light. And as I emphasized, there is a close relationship between the wavelength and frequency of a wave. If waves are moving at a particular speed, the product of the wavelength and the frequency equals the speed that the wave is traveling. And in the case of and so here we're using the Greek letter lambda to represent wavelength. Lambda is sort of the Greek equivalent of the letter L, and we use L for length. The Greek letter nu is used to denote the frequency of the wave. So wavelength is a measure of how the wave oscillates in space. Frequency is a measure of how the wave oscillates in time. And when you multiply those together, you get the speed of the wave. And if you're talking about light, the speed of light is exactly 299,792,458 meters per second. So about 3 times 10 to the 8 meters per second is the speed of light. And so light is just a part of a larger spectrum of waves called the electromagnetic spectrum. And the visible light is sort of in the middle of this larger spectrum. Visible light has characteristic wavelengths less than a micrometer, and so they are roughly that length is roughly the size of protozoans, and the corresponding frequency for visible light is around 10 to the 14 cycles per second, or 10 to the 14 hertz. Then if we go to somewhat longer waves that have a shorter frequency or a lower frequency, we get below red, we have infrared. The word infrared literally means below red, and infrared waves are they have a longer wavelength and a lower frequency than visible light. And then moving below infrared, we have microwaves. Microwaves range in size from centimeters to meters. And then at even lower frequencies, we have radio waves. Radio waves have lengths on the order of tens to hundreds to even thousands of meters, and they have much lower frequencies to go along with that. Now, on the other side of the spectrum, above visible light, we have ultraviolet. So ultraviolet literally means above violet, and that has those waves are shorter than visible light and have a higher frequency. Beyond ultraviolet, we have X-rays, and beyond X-rays are gamma rays. And so this gives us sort of a survey of the electromagnetic spectrum. And of course, the part of that that's most familiar to us is the red, orange, yellow, green, blue, indigo, violet of the visible spectrum.